if we consider this in the form of a comma b, b should be greater than 6. So that means we can select from these three because b is less than 6 here. We can clearly take the elements of the form 0, 0, 1, 1, 2, 2 until 12, 12 because 0 is a multiple of 4. So we can use two methods here. One is to show that the function is 1, 1 onto bijective, hence it is invertible, and writing the inverse of x. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. So here we are at the revision classes of your second PUC chapter, Relations and Function. So let us see the chapter-wise weightage for your board examination from this chapter. So here I have divided this into your question paper pattern, that is part A, part B, part C, part D and part E section. We know that in part A we have MCQs and fill in the blanks, part B 2 marks, part C 3 mark question, part D 5 mark question, and in part E we'll be having 1 4 mark and 1 6 mark question as an options. Now in this chapter Relations and Function, you will get 2 MCQs from the chapter Relations and Function and 1 3 mark question. Basically it will be on relations, that is to verify the equivalence relation, and 1 5 mark question and it will be on function. So in total you can expect 10 marks from this chapter. So let us take few objective questions, that is in the form of multiple choice question. So the first question is, a relation R in the set 1, 2, 3 given by R equals 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, 1, 3. Then R is, the option is reflexive but not symmetric, reflexive but not transitive, symmetric and transitive, neither symmetric nor transitive. So here, if we see the relation set here and the set A is 1, 2, 3 here. So we have all possibilities of 1, 1, 2, 1, 3, 3, hence the given relation is reflexive relation. Whereas if you come here 1, 2, you have 2, 1, so it satisfies symmetry. But here 1, 3 doesn't have a pair 3, 1, so we can say it is not symmetric. And when we come for the transitive relation, we can see 1, 2, 2, 1 has 1, 1. Similarly, if you take 1, 1, 1, 3, you have 1, 3. But see here, if you have 2, 1 and 1, 3, you don't have the relation which has the element 2, 3 here. So we can clearly say that it is neither symmetric nor transitive relation. Next question. A relation R in the set 1, 2, 3 given by R equals 1, 2, 2, 1 is. So clearly the given relation is a symmetric relation. But let's see whether it is reflexive or transitive. Is it reflexive? No, because it doesn't contain the ordered pair in the form of 1, 1, 2, 1, 3, 3. Since 1, 1 is not there, it also doesn't satisfy the transitive relation. So among the options here, reflexive but not symmetric, symmetric but not transitive, symmetric and transitive, neither symmetric nor transitive. So we can clearly say option B is the correct answer, that is it is symmetric but not transitive. Next, let R be the relation in the set N given by R equals A, B, A equals B minus 2, B is greater than 6. So according to the given condition, choose the correct answer. So which ordered pair belongs to the relation set we need to identify? 2, 4, 3, 8, 6, 8, 8, 7. So from the definition given here in the relation set, A is equal to B minus 2 and B is greater than 6. That means the value of B should be greater than 6. If we consider this in the form of A, B, B should be greater than 6. So that means we can select from these three because B is less than 6 here. Now they have given the relation A is equal to B minus 2. We can also write B is equal to A plus 2. So if you take the value of A as 3, then B should be 5, which is not possible. If you take C here, if you take A as 6, then B is 8. Yes, this is satisfying your answer. This is cannot be 8, 7 because A should be less than B. So the correct option is 6, 8 belongs to R. Next we have, let f from R to R be defined by f of x is equal to 1 by x belongs to R, then f is 1, 1 onto bijective, f is not defined. So a function which is both 1, 1 and onto is bijective, but here the x value should be taken from the domain which is a set of real number. But we know that x cannot take the value 0 when it is in the denominator. So clearly f is not defined is the correct answer. Next, find the number of all 1, 1 functions from set A 1, 2, 3 to itself. So when I say it's a function from A to A, so we have 3 elements here and 3 elements here. So that means 1, 1 function means we have to relate them in a distinct form. So for n element, you cannot have the same images and 2 elements cannot have the same images here. So therefore, here the 1, 1 function from set A to set A, that is equal to 3 factorial, which is 6. So it always in the form of n factorial, because when we say 1, 1 function, here the images are distinct. So therefore, when we consider set A to itself, it is always n factorial form. Now here we have n is equal to 3, so therefore it is 3 factorial, whose value is 6. So let's look upon 3 mark questions here. So basically I already told you here 3 mark questions will be on equivalence relation. Sometimes you can expect from composition of functions also. So let's take few questions on them. Now determine whether the relation R in the set A 1, 2, 3 to 14 defined by R x, y, 3x minus y is equal to 0 is reflexive, symmetric and transitive. So let me recall the definition of your reflexive, transitive as well as symmetric relation. So reflexive relation means for all A, there should be an ordered pair in the form of A, A. And symmetric, if you have A, B in the relation set, then there should contain an element B, A in the relation set. Now coming to the transitive, if A, B, C belongs to the set R, then A, C should also belongs to set R. So let's see whether this will satisfy the given condition. Now here, according to the given relation set, we can clearly see here y is equal to 3x and all your x and y belongs to the set A, which contains the numbers, the natural numbers from 1 to 14. So if I write the relation set here, and if I take x is equal to 1, then y is 3, x is 2, then y is 6, x is 3, y is 9, x is 4, y is 12. So we can't take 5 because it is 5 3s are 15, which exceeds the set A. So therefore, these are the only element in the relation. Now, since the element 1, 2, 3 to 14 we have, clearly we can say 1, 1 does not belongs to R. So we are concluding that R is not reflexive. Or we can generalize the statement for any A belongs to the set A. So there is no A, A belongs to set R. So therefore, it is not reflexive. So let's take an example of symmetric relation. Let me take 1, 3 belongs to R. So here we have 1, 3 belongs to R, but 3, 1 does not belongs to R here. So we can clearly say this is not symmetric relation. So let me consider these 2 elements. Now 1, 3 belongs to R here. 3, 9 also belongs to the set R. But clearly you can see here 1, 9 does not belongs to R. So therefore R is not transitive. So we can conclude this here as R is neither reflexive nor symmetric nor transitive. Next question. Show that the relation R in the set A, x belongs to integers and it lies between 0 to 12 given by R is equal to A, B in the form modulus A minus B is a multiple of 4 is an equivalence relation. we should choose the elements a comma b from the set in such a way that their difference under the modulus is a multiple of 4. We can choose 0, 4, 4, 0, 4, 8. 0, 5 cannot be chosen because their difference is 5 and 5 is not a multiple of 4. So we should pair an element in the form so that their difference is a multiple of 4. If we take the element 1, then we can pair 1, 5 as well as 5, 1 because the difference is 4 and 4 is a multiple of 4. So we have to pair in such a way that it satisfies the given condition. Now since we are pairing the elements which satisfy the given condition, let us see whether it is a reflexive, symmetric as well as transitive relation. Now for reflexive, we can clearly take the elements of the form 0, 0, 1, 1, 2, 2 until 12, 12 because 0 is a multiple of 4. So that means we can take the difference in the form of modulus a minus a. So modulus a minus a is a multiple of 4. So this implies a comma a belongs to R. Now for all a belongs to this set A, we are getting a comma a belongs to R. So therefore it is reflexive relation. Let's take an example of symmetry. Now let me take two numbers. Let me take 1, 5. So modulus 1 minus 5 also belongs to R. Modulus 5 minus 1 also belongs to R because their difference under the modulus is 4 and 4 is a multiple of 4. You can also check with other numbers whose difference is in the form of multiple of 4. So therefore we can clearly say here for all a comma b belongs to R, this implies b comma a belongs to R. So clearly R is symmetric relation. And let's take an example of transitive relation. So let us take 4, 8 and 12. If I say 4, 8 belongs to R and 8, 12 belongs to R, obviously 4, 12 whose difference is 8 and it is a multiple of 4 belongs to R. So therefore you can take any ordered pair which satisfy the given condition, that is modulus a minus b is a multiple of 4 will belongs to the set relation. So let us generalize this statement. So that is for all a comma b belongs to R and b comma c belongs to R. So we can clearly see here modulus a minus b and modulus b minus c is a multiple of 4. So let's take the sum of these. So then a minus b plus b minus c under the modulus will give you modulus a minus c, which will become a multiple of 4. So which implies here a comma c belongs to R, which is satisfying the transitive relation. Hence, this relation is an equivalence relation because it is satisfying the condition of reflexive, symmetric as well as the transitive. Check whether the relation R in R, that is real numbers, is defined by a less than or equal to b cube, is reflexive, symmetric and transitive. So let us take an example. Here a is less than or equal to b cube. We should take any real number. So now half, let me take a fraction less than or equal to half cube. So 1 by 2 less than or equal to 1 by 2 cube, that is 1 by 8. This is equal to 1 by 8. So yes, 1 by 2 less than or equal to 1 by 8. Is it true? No, because 1 by 2 is more than 1 by 8. So if 1 by 2 is less than or equal to 1 by 2 whole cube, then it should imply that 1 by 2 comma 1 by 2 should belongs to R. But here this is not satisfying the condition. So therefore it does not belongs to R. If you take whole number, suppose 2 less than or equal to 2 cube, yes, it satisfies the conditions. So for any whole number, this will satisfy your condition, but when it comes to the fractions in the set of real number, so it cannot happen. So therefore, we know that for all the A, there should be A comma A in the R. But here, the condition is not satisfying for fractions. So therefore, this is not reflexive. Now, coming to the symmetric. So symmetry cannot happen. Clearly, if I take the same example, so if I take 1 by 2 is less than 1, then I cannot say 1 is less than 1 by 2. So, it contradicts the relation less than. So, therefore, this is not symmetric relation. Now, let's take an example for transitive relation. So, let's take fractions here. 1 by 2 less than 1 and 1 less than 2. So, 1 by 2 less than 1 is possible, 1 less than 2 is possible. If you take it in the form of 1 cube as well as 2 cube, it is true. So, when it comes to the fraction, transitive can hold. So, let's check with the example of whole number. Let's take 100, 100 comma 5. So, according to the given relation, A should be less than or equal to B cube. That means here 100 is less than or equal to 5 cube. So, 100 is less than or equal to 125. So, let's take 5 comma 2. 5 comma 2. So, this implies 5 less than or equal to 2 cube. That is a 5 less than or equal to 8. So, now here we can clearly see 100 comma 5, 5 comma 2 is possible. Let's check for 100 comma 2. 100 comma 2, which is 100 less than or equal to 2 cube. Does it satisfy the condition? No, because 100 is not less than or equal to 8. So, which means this does not belongs to set R. So, therefore, it is not transitive relation. So, clearly, by taking an example of numericals or generalizing the statements, we can clearly say the set R is neither reflexive nor symmetric nor transitive. So, apart from equivalence relation, I told you sometimes you can expect the question from composition function. So, here we have such type of question. Find G naught F and F naught G, where F and G are the domain and codomain is from the set of real numbers to real number, given by f of x is equal to cos x, g of x is equal to 3x square. Show that G naught F is not equal to F naught G. Clearly, we know that the composition of function is not commutative. So, we need to prove this here. So, now let's take G naught F, which means G of f of x. So, in f of x is given in the form of cos x. So, we'll write G of cos x. And G of x is written in the form of 3x square. So, that means in the place of x, you have to write cos x. So, we will get 3 cos x whole square, which means cos square x. So, G naught f is 3 cos square x. Now, let's take f naught g. So, f naught g means f of g of x, so which is f of 3x square. So, any x under the function f is written in the form of cos x. So, this becomes cos 3x square. So, clearly this is 3 cos square x and this is cos 3x square. So, we can say G naught f is not equal to f naught g. Now, let's look at the 5-mark questions. So, I told you in 5-mark questions, there will be a questions on inverse of a function, that is f of x is equal to 4x plus 3 form, or they may ask you for bijective, that is to show that whether the function is 1, 1, onto and bijective. Now, let's take this question. Prove that function f from n to y defined by f of x is equal to 4x plus 3, where y is equal to 4x plus 3 is invertible. Also, write the inverse of f of x. So, we can use two methods here. One is to show that the function is 1, 1 onto bijective, hence it is invertible, and writing the inverse of x. The other way is to find, just to show that G naught f and f naught g are identity function and write the invertible function. So, now we have here f of x is equal to 4x plus 3. To show this function as 1, 1, so let's take it as f of x1 is equal to f of x2. So, which means 4x1 plus 3 is equal to 4x2 plus 3. So, we can cancel 3 on both sides. Later we can cancel 4 on both sides, which implies x1 is equal to x2. So for all f of x1 is equal to f of x2, we are getting x1 and x2 are the same. They are one and the same. So therefore clearly this is 1 function. Now we have y is equal to 4x plus 3. So this implies, so x is equal to y minus 3 by 4. This x belongs to the given set n here, because by looking at the condition y here, we can clearly see x belongs to the codomain. So that means for every element in the set y, we have one element in the domain. So therefore, clearly this is an onto function. Now f is 1 and f is onto. This implies f is bijective. So if f is bijective, it is invertible. So this implies f is invertible. Thus, we can write f inverse of x exists. F inverse of x exists. So here, this f inverse of x can be written in the form of x minus 3 by 4. So this is the inverse of the given function. Next question. Check whether the function f from R to R defined by f of x is equal to 1 plus x square is 1 onto or bijective. Now, f of x is equal to 1 plus x square. So let's take f of x1 and f of x2. F of x1 is equal to f of x2. So instead of x1 and x2, I'll take f of minus 1, which is same as f of 1, because f of minus 1 and f of 1 will give you the same value, because minus 1 whole square is also 1, 1 square is also 1, whose value is 2. But clearly we can say minus 1 is not equal to plus 1. So the images are same, but the domain elements are not same here. So clearly f is not 1 here. Now, to see whether it is an onto function. So clearly when I say f of 1 plus x square here, x square is always greater than or equal to 0. And if I add 1 on both sides, it is always greater than or equal to 1. That means it is always the positive number. So what about the negative real numbers here? So the negative real numbers in the codomain are completely free. They do not have any pre-image element in the set R. So therefore clearly it is not onto also. Now since it is not 1 function, not onto function, it is not bijective also. Next question, let A is equal to R minus 3. That means a real number set which does not contain 3, and B is equal to R minus 1, the real number set which does not contain 1. Consider f from A to B defined by f of x is equal to x minus 2 by x minus 3. Is f is 1 on to justify your answer. So let's check this property with f of x1 is equal to f of x2. So then we'll get x1 minus 2 by x1 minus 3. So x2 minus 2 by x2 minus 3. Cross multiplying we'll get x1 x2 minus 3x1 minus 2x2 plus 6. And here again x1 x2 minus 2x1, next minus 3x2 plus 6. So plus 6 x1 x2 plus 6 get cancels on both sides. So we have minus 3x1. So let's shift minus 3x1 to that side, and let's take 3x to this side. Then we'll get 3x2 minus 2x2, which is equal to 3x1 minus 2x1, which implies x2 is equal to x1 or x1 is equal to x2. So clearly it is satisfying the definition of 1 function. So therefore this is 1 function. Now let's check for onto function. So we have y is equal to x minus 2 by x minus 3. So let's cross multiply, then it is xy minus 3y is equal to x minus 2. Now let's shift here. Xy minus x is equal to 3y minus 2. And if you take x as a common factor, then it is y minus 1 is equal to 3y minus 2. X is equal to 3y minus 2 divided by y minus 1. So here y cannot take the value 1. Now clearly here b, that means y is in set B and it is satisfying the condition r minus 1. Also, we can see for every element in set B, clearly we have the pre-image. So therefore here x belongs to set A. So therefore it is onto function. Now since the given function is 1, 1 as well as onto, it also satisfies the bijective condition. But here they have asked us to check only 1, 1 and onto. So let's stop writing or concluding the statement that f is 1, 1 and onto. So these are all few important questions for your examination from this chapter. So let's take up next chapter in the next session. Until then, keep watching, keep learning and keep exploring. Thank you.